Okay, so let me introduce the second speaker of this session, Professor Perla, Gustavo Perla, and he'll give a talk on dynamical system for shell shows.
Thank you very much. I want to thank the organizing committee for the kind invitation to participate in this event and to have the chance to re-encounter very good friends. I want to tell you some recent results that we got in collaboration with Fabiana Travesini on properties, special properties of shallow shells. These shallow shells, in this case, are four equations, four nonlinear equations, evolution equations, dynamical system, nonlinear equations, which act in a manifold, no? A very special manifold because it's a shallow, very shallow manifold. And the properties will say that there is some proximity of the model with another model, as long as you introduce some special parameter. Another model which still acts on the manifold. And the second is to study the asymptotic behavior of the total energy as t goes to infinity. Okay, these are the two main results. So the easiest way to see that you want to think is just a graph of some smooth function, no? Which is defined in a region omega R2, but it's better to follow all the things with in terms of manifolds, and so the calculus of manifolds are available. So we go to that notation. So for beams or for plates, all the inelasticity, all the models are based on how the deformation is of the middle X in a beam, the middle plane, or in shells of the middle surface. No? All the movements are on this middle surface, and there is going to happen all these changes, modifications. So we have, as in a minute you will see that I have a smooth manifold in here, M, and then each point in here, when the deformation happens, this point will move somewhere. And there are two things in here. One is the transversal deformation displacement, and this is going to be by a function W. And there are two functions here in the plane at time t, and this will be given by two functions in here, which are the in-plane displacements. And these two functions are going to be u and v, which in the moment I'm going to write this as big U. And so we have two functions, three functions, and the heat. There are going to be some thermal effects. So we have four functions which will be included in the model. Okay? So this is just to give some information that in the case of shallow shells, the function W is going to be fairly small. Okay? So while you keep modeling any shallow shell, you have to take in consideration several basic rules which are mentioned right there. The moderate bending, the Kirchhoff hypothesis, the shell is very thin wallet, and so on, some other ones. This development of shells, there are several different kinds of shells, were basically by the Russian school, the German school, and later on by Marguerite, Blasot, Novochilov, and other ones. Okay? So I will use the language of the calculus on manifolds available in this book, for example, of Michael Taylor, and I will use the Laplace-Beltrami operator and the B-harmonic Laplace operator. Okay? So these are the basic things of calculus and manifolds. I will use eventually in my discussion. This is the model. The model is this one here. This big U is this, it has two functions, small u and small v. So we have two equations here. It has a matrix 2 by 2 symmetric matrix. This is the divergence of the matrix, divergence of the first line and the second line. No? This is the equation I'm going to include for the second part of the talk, but in this first part, it's not necessary to write that. This is the function which is described by this transversal displacement. Here we have the V-harmonic Laplace-Beltrami operator. And here you have this term. This K1 and K2 are the curvatures of the manifold. Okay? This is the heat, the thermal effect. And the nonlinearities are included in this B1 and B11 and B22 and here also. The problem depends very much on the conditions that you want to study. And in this case, take the simplest case, which are clamped boundary conditions, and some initial conditions in some functional space. These are the B1, B2, you see? These ones in here, this is a symmetric matrix. Here you have the nonlinearity quadratic for these big ones in here. Quadratic here, and eventually you have the other divergence in there. The model is being around for quite a long time, at least 50 years or more. And to simplify my discussion here, several parameters I'm just choosing to be one, except this one here, the modulus of elasticity. Okay, the constant between 0 and 1/2. These are the clamped boundary conditions that I'm going to consider. Both results in here are very sensible to the boundary conditions. It's an important case which is left to study later. The initial conditions are these, in some space that I'm going to mention in a minute. And global existence of regular and weak solutions are well known by standard methods, but the uniqueness always was very hard for this model, as it was also for von Karman plates, because the Gromwall inequality does not hold. And the nonlinear terms are not local ellipses in the energy norm, so it requires another further idea, which Sedenko got a very pioneer work in this case, for the uniqueness without thermal effects. And Fabiana Travesini just used the technique in there to do it for this model that I'm talking to you now. Okay, so we are in good shape to having global and existence of regular and weak solutions and uniqueness, no? Now, these are the two problems that I was telling you. One is the proximity, how near is our model, this model I told you, and when you introduce some singular perturbation. And the other one is the asymptotic behavior of the model, because due to the thermal effects I have dissipation, and I included the other one for the first two wave equations, no linear. No? And this is the perturbation to solve the first problem I want to tell you. This is a singular perturbation in here. Well, this is not so interesting at this moment. I can put it this or not. But here, you see, this B1, B2, B1, B22, and B12, I have modified by this epsilon in here, and this epsilon in here. When epsilon is 1, it's just the original model without any singular perturbation. Also this one here, they have an epsilon here. We were more or less, motivated by an earlier work that Andy Maida. Andy Maida considered about 20 years ago, more or less, some singular perturbation for the busyness, rotating busyness equations in a singular way, and passed to the limit to get geostropic, some kind of geostropic model that today is very much work. And so we consider this singular perturbation with the same boundary conditions in here that we had for the other product, and the same initial condition. To simplify, I'm going to use this. I'm not going to put epsilons in my initial data, okay? Independent of epsilon initial data in here. Then the final result I want to tell you, yes, the outline, how do we get, is this one here. As epsilon goes to 0, then this function W, which depends on epsilon now, and the thermal effect, the temperature depends on epsilon. When epsilon goes to 0, they approach weakly to the solution of this coupled system. This is like a Timochenko equation, you see, because this term in here does not depend on x. You have some function of t here, multiplying this, the same function of t multiplying this, the curvatures, sum of the curvatures, and this one here. So it's like a system of equations on a manifold, okay, which maintain the curvatures, but it's much simpler than the other one because we know how to treat the Timochenko's type equations for several years. So for that system, we find that, of course, we have the same boundary conditions as the original one with an epsilon, and maintain the initial data because I put it independent of the epsilon, okay? Now, so this is the theorem. I'm not going to give you detail, but I'm going to give you an outline. How do we get it? So the theorem says that I perturb my model. I have these two curvatures in here, so the space on the manifold, and consider the initial data, in this case a weak solution I'm talking about. This approach weakly start to this triple, which this C and this W solve the equation that I wrote before, no? And so the idea of the proof is the following, yes, no detail, please. So the total energy associated with that model that I'm considering is this one here. I'm not going to write epsilon again here, so trying not to confuse, but U, V, W, and the thermal effect all depend on epsilon, no? I put an epsilon here, so this is the total energy. Everybody depends on epsilon. These ones too, also these ones too. So due to the structure of my system, it's easy to prove that this holds. This is the dissipation due to the thermal power in the manifold, and this is the one, the UT that I included in the model. So the total energy is bounded, independent of epsilon, because this epsilon varies between 0 and 1, and the initial data does not depend on epsilon. And therefore, I have several sequences in epsilon which are bounded, and of course, we can use our functional analysis and take subsequences which convert to some functions weakly stopped. And then the linear part of my system, easily I can convert it to something which in these functions, no? The only difficulty that we have in the following is to detect the convergence of the nonlinear term and who is the nonlinear term, right? Then, so you see, I keep finding the convergences, subsequences of the functions here depend on epsilon. Here, I continue doing that. I use Korn's inequality, and I get this information, and I continue doing my possible inclusion of Sobolev inclusions in the manifold, and I get some convergences in here, right? So this is standard. Like, as I told before you, the linear part is all set, no problem. And the only thing is that I have to pass to the limit in the nonlinear part. Thanks to the structure of my total energy and by boundaries of these functions in H20, then I can use the compactness criteria of Van Leon's and take subsequences which converge strongly. And keep going in my information, and then I get all these convergences in here, which is going to help because I have weak and strong, and therefore I have weak convergences on many subsequences. Then I continue in my procedure to detect with the nonlinear limit. No, I get the following information on these big B's that you see in here. This one is bounded, so with this goes to 0, with this goes to 0. So B21 and B12 go to 0 weekly, star. And then I consider adding to all the math information. This D epsilon is defined in this way. This converges strongly to this. This is in W1 infinity in the manifold, so there is no problem for this convergence. This goes strongly in H1 in the manifold. Because of Korn's inequality, these two in epsilon, they approach to this. So this approach to this. Okay? So, on the other hand, just I have these convergences also because of the discussion before. And finally, this approach to this one here. And conclusion. We have the convergence that I needed. The nonlinearity converges to something which the linear part was already all set. Just the nonlinear part gives me this one for this function d of t, right? So I only have 2 minutes to tell you who is d, detect d, right? And I'm going to show you that d only depends on t, does not depend on x and y, and has a special structure depending on c. Then I have certain convergences that I take a look again. And now I use the first equation. The first equation I have by the energy boundedness, you have that this is bounded, with this goes to 0, this goes to 0. If that goes to 0, the divergence goes to 0, no, because of the first equation in there. No? You see, because of the first equation I have, this goes to 0, this goes to 0 already. So this goes to 0, but by the discussion that I told you in the previous transparencies, this was going weakly to this function. This diagonal here on the other side are 0. So the divergence of this goes to the divergence of this, and this gives me that these two conditions hold. Then D only depends on T. If D depends on T, is the first information, and now I have to find the shape of T. That is easy now. I integrate this on the manifold, the epsilon, gives me this. There is one term that vanishes in there because the U satisfies the, is 0 on the boundary, no? then therefore the first two terms vanish on the boundary because I had a divergence of them. And then this is part of the integral of d. This piece in here converges to this, and this converges to this already. So I have information. This converges to this expression. And for the other side, d epsilon converges to d. And then I take out of the integral, and I only get the measure of the manifold, the area in this case, the area times d of t. If I put together this with this, then I have the shape of d of t, which is exactly this. I plotted in the equation that I found, and then I solved. I had the kind of limit system that satisfies c and t. The initial conditions are already satisfied, and the initial conditions are easy in the standard way to verify that they are okay. So this is the outline of the proof of this thing. The next result in 2 minutes, I just want to tell you in outline what was the procedure. I have the total energy. I wrote it here again. In this case, I'm not even writing. I'm putting epsilon equal to 1. I don't need the epsilon. I just consider the system with epsilon equal to 1, the original system of 4 equations, with the same notations as before, the same initial conditions, the same boundary conditions. So the theorem in my case is this one. What I have with my global, this is essentially theorem 1 with the notation that I used before. If I fix an R as large as you want, then the total energy decays locally exponentially, in the sense that there are 2 constants which depend on R, and this one here depends also in the curvatures, such that the total energy, well, I'm sorry, this epsilon is 1 for me to simplify. I simplify in one page, I'm not simplifying the other. So the case exponentially. Exponentially, as long as the initial data is bounded, is in that ball, right? So you fix an R, and then you take all the possible initial data less than in that ball, and then you have this decay in that way. As long as I have some conditions on the curvatures. We were trying to see if this is really necessary, changing the proof of another one, but it came out some other condition which is almost similar to this one here. Perhaps it's essential, I don't know. Then the idea of the proof is just to use modified multipliers. You use modified multipliers based on earlier work that many people have done for the von Karman equation for plates, not for shells. And then you divide the total energy. I'm sorry, I put epsilon in here, which is not necessary if I not pass to the limit here in epsilon. So you have this from the dissipation. The dissipation of the energy, you have this thing here for any S and T. And in order to prove the decay using multipliers, only one point comes very hard. Very, very hard. Is to try to get bounds for the integral of L2 of this Laplacian of U on the boundary. Which does not come from the usual trace theorems. You have to work it out in a very, very tiring way. And this was the key of the proof. After you have that, then, well, this is a lemma in order to prove that stuff. And this is another technical thing trying to get a bound for this one. This is the harder term, you know? I have to bound this by some constant which depends only on T, and the initial energy. And then you use heavy multipliers, and finally, after a lot of work, then you find that this one here that it is on the boundary, it's bounded by this. All these terms are bounded by the previous discussion. So you have that. I'm going to pass the transparent because I have very little time. You divide the energy in two pieces. One is this one here with terms which are reasonable, and the other one contains these harder terms. And you keep working with the multipliers, and then you will try to reach two inequalities. Let me see if I, here it comes the conditions. You see, in some of these inequalities that I have this condition in here that it has to be bigger than 0, and therefore that gives me this condition that I have for my curvatures. I cannot avoid those. You see, this condition comes from there. And then you prove this inequality, and you have already the integral of 0 to t d1 in terms of u2 put together information, and you are going to get an inequality of this type. You see, from there you get this inequality, which is less than 1, and this depends only on the radius of the ball that I fix it. And this is does not depend on nothing, just a general constant. And then from then you get this expression, because the problem is well posed, and you use the semi-group property, and then you find the exponential decay. So this is the summary of the lecture. And then I have some references. Basic reference that we use is one here from La Sieca and colleagues on some other kind of nonlinear shells, shallow shell, but not the ones that we are treating here. La Sieca also has for many things for plates, and here they have problems of von-Karman equation with thermal effects. Very good papers. I have some previous one for plates too with Enrique Suazua and with Ademir Pasotto, who is here. This is the original work that he announced it here, Sedenko, and he published here later on. And he has nice results also. He has a book, this one here. Thank you very much for your attention. Thank you.